3.4, we're looking at multiplication of whole numbers, and in particular, all of these sections kind of follow the same format. We talk about some applications, like how we can think about them, right? So in multiplication, we talked about repeated addition. We've talked about the array model, the area model, and a Cartesian product model, and you did some examples. And the next thing that we've done in each one of these sections is talk about properties and decide if and when which properties hold within which operations. So we're going to look at each of the properties that we saw happen and add a couple more to them. So the first property is the closure property. Now we saw the closure property show up for addition. It says if you add any two whole numbers, you get another whole number. And we saw it fail for subtraction, because sometimes you can subtract whole numbers and not get whole numbers. For multiplication, it succeeds again. It is a property. If you multiply whole numbers, you get a whole number. Okay, so the closure property works for multiplication. Commutative. We saw commutative work for addition, fail for subtraction. It works again for multiplication. The commutative property says the order in which I multiply doesn't matter. And that's always a wonderful thing, because it means we have to memorize half the number of facts. I mean, truly, right? Yeah. So we have the order of the multiplication, A times B is equal to B times A. Associative property has grouping involved. Again, it worked for addition, it failed for subtraction, and once again it works for multiplication. So if I have three numbers, A, B, and C, that are multiplied, it doesn't matter if I multiply A and B first, or if I multiply the B and C first. I can group them together and multiply whichever pair I'd like, and I'll get the same quantity at the end. And that's really nice, actually, because if you're aware of that, and you'll see some of our properties used in some of our strategies later on, our algorithms, sometimes we can make better choices in which groupings we do to make our multiplication easier for us. Identity. Now, we had an identity property for addition. We did not have one for subtraction. What was our identity element for addition? It was 0. Okay, so it's different for multiplication. We have an identity property. You might want to write in that this is the multiplicative identity property, because the number's not the same. Our additive identity was 0, but our multiplicative identity is actually the number 1. Because when I multiply by 1, either A times 1 or 1 times A, the value A remains unchanged. If remember, that's what it was with 0 when we did addition. 0 plus A plus 0 is A. It doesn't change. So we have a unique number that does that, the number 1. There's a couple more that we have. One of them is the multiplication property of 0. So this is not an identity, but it is a property of multiplication. And it simply says that if I multiply by 0, I get 0. Right? And then the last one combines multiplication with addition or multiplication with subtraction. And it's a distributive property. It says that if I have the number A multiplied by the quantity that's A plus B or A minus B, I'm able to distribute that A through and multiply it by each of the individual pieces, and then do the addition or subtraction. Now, do you have to do that? Well, no. It has to do with whether or not it's convenient to do so. And it becomes convenient to do so usually when you're working with algebra, where you can't combine the pieces that are inside, right? They're not alike. So does it make sense to do it with whole numbers? Well, not usually, but it's still true. Okay? So what I'd like for you to do is I think there's 6 of them. 6 different examples. I'd like for you to go through, and I'd like for you to identify which of the properties is being used on which examples. And this is not a one-to-one correspondence. Okay? There are 6 properties, and there are 6 of these down here, but that does not mean that there's one for each one. In fact, I don't think there is. No, there's not. So as you're going through, if you repeat something, that's going to be expected. There is at least one that gets repeated. Okay? So go take a look at A through F. Once you have all your A through F done, compare notes with somebody nearby and see if you've got problems or answers that match. Okay, you guys ready to see what everybody thinks as a whole?
Sure.
Let's do it. What did you think that the first one was?
The property.
Yeah, the multiplication, and I'll abbreviate as I go, but property of 0. How about the second one? It's commutative. I don't want you to think that just because you see commutative, just because you see parentheses, it means it's associative or it means it's distributive. It's not, right? This is the commutative property. How about C? Ah, that one's associative, though. That's not a word you want to abbreviate. How about D? Yeah, it's identity. Specifically, yes, thank you, the multiplicative identity. Okay, so make sure to specify that one when you're using it, since there are different numbers we're talking about between additive and multiplicative. We don't need that quite so much on the other ones because the properties are the same, like they work the same way. This one simply has a different value we want to be careful of. How about E? Right, that one's distributive. And F? Which one? What'd you say, Kaylee? Distributive? That's what I'm hearing. Mackenzie wasn't sure, or Kinsey wasn't sure. Yeah, I heard your discussion. It is distributive. So those of you who thought that that's what it was, you are right. It is a distributive property. I overheard Autumn saying that she noticed that it was distributive because there's multiplication and addition inside of it. That's a good observation. It feels a little bit funny, but you see this 1 plus 2 still grouped together. And in here you see the 1 plus 2 at the beginning. And what they've actually done is they've applied it like this. Can you see it now a little bit better? That's what's going on with the distributive property there. But it is just distributive property. That's correct. All right. This is a question about properties. It would be a section C kind of a problem. JJ claims that the following is true by the distributive law where A and B are whole numbers. 3 times the quantity A times B is equal to 3 times A times 3 times B. How would you help him? First you have to decide, is he right or wrong?
It's wrong because you're not multiplying. Well,
Is he right or wrong? Kinsey's changed her decision from wrong to right.
well, because I feel like it's too much multiplying.
Okay, you feel like there's too much multiplying going on?
But I also don't know where the addition, like, where your addition.
Would you
Ooh, so what does it seem like is missing, Kaylee?
And addition.
There seems to be an addition missing.
wouldn't you add those since I'm multiplying them?
If they were added to begin with. It's almost like you're looking at the left-hand side of the equation, 3 times the A plus, or times the A times B. And he's saying if I try to do the left-hand side, it will become the same thing as the right-hand side. All right, it's like his question is starting out here, and this is his work after it. Is that what his work after it should look like?
I mean, yeah.
Is it? All right, I want you to try an example.
I don't know. I think you need to. put
Here's what I want you to do. I want you to try something. I want you to take a pencil. I want you to write down A is equal to 2, and B is equal to 4. Okay? So I want you to do the left-hand side, 3 times 2 plus 2 times 4, and figure out what the left-hand side is. And then I want you to find 3 times 2, and then times 3 times 4. Because if he's correct, these will be equal. What's the first one? What is 3 times 2 times 4? That's 24. On the one below, I have 6 times 12. So what's 6 times 12? So what can you tell me about those numbers? These are not equal. Can Can you tell how much they're different by? Or how they're different? 3 times. 24 times 3 is 72. In particular, this additional 3 that got multiplied through, right? So, one way you should be able to help him is at least by giving him an example that shows it doesn't work. And in fact, most numbers are going to fail to work here. There's nothing special about 2 and 4. Sometimes we have to be very strategic in how we choose our values. We don't have to be strategic on this one. So this one fails. So I think one good idea is to show an example. Where it doesn't work. And that's our example here. And I'm going to come back to what Kaylee mentioned before. She wasn't quite sure how to finish her statement, but you were definitely on the right track. Distribution involves multiplication over addition or subtraction. And I realize the words I'm saying sound grammatically correct and the words I'm writing are not quite because I'm abbreviating, but I think we're okay with that. It's multiplication over addition or subtraction. This problem is all multiplication. In particular, this 3 times A times B business like that could in fact be rewritten. It just wouldn't be rewritten the way he is supposing. The only rewriting that we can do from a property standpoint, or the simplest rewriting we can do from a property standpoint, is to regroup the symbols, right? Now we may or may not want to do that, but it's the associative property. But can you see why he made the mistake? How it feels kind of like the distributive property in the way it's set up, right? So it's not that he doesn't know what he's got going on. He's just identifying something in a pattern in a slightly incorrect way. But it's a pattern he's seen before. All right. It's going to feel like we're taking a little bit of a deviation, but we mentioned at the beginning that one of the perspectives of multiplication is that it's repeated addition, okay? We're going to take a look at properties of exponents as we do the rest of this section, and then we'll get to some other algorithms. If you have taken an algebra course recently, or if you've taken proportional statistical reasoning recently, some of these are going to feel like, I think I just did that. We do it in those classes too. So the first one says that if I have, so I'm going to show you the 4 properties first, and then I'm going to show you justifications for why they work. All right, so A times A times A times A times A, all of this is repeated multiplication, n times. So A to the power of n means multiplying A together n times for a rational number A. This is called the base. A is called the base, excuse me, and the n is called the exponent. When we have A to the m times A to the n, we add the exponents, A to the m plus n. So then on number 2, what do you suppose is going to happen when we divide them? We are going to subtract. 3 looks kind of like 1, but it doesn't have that repeated base, right? Their base is only there 1 time, so it's A to the m, and all of that has a power to the n. So what do I do with the m and the n? Yeah, we do. We multiply. And then number 4 actually feels a lot like that distributive property we had before. When A and B are multiplied together, which they are here, it doesn't work if it's added or subtracted. If A and B are multiplied, we can distribute the power of M to each of the A. Oops, I don't know why I wrote that. And to the B. Okay? So we're going to look at why that works. So this is the property that I'm trying to justify. It is important for you to realize I am not proving what I'm telling you. I'm just giving you a justification for why it would work that would be sufficient for children in your class at this age. Okay? This is not a proof. This is just a justification by example. We're going to use a cubed times a squared. So what does a cubed mean? A 3 times like this. A times A times A. And what does a squared mean? A 2 times. So I have 3 of them and then I have 2 of them. How many is that total? Right, there are 5 total. So this would be a to the 5th. And how in the world do you get from 3 and 2 to 5? You add them, right? So the kid in your class is like, but why? Why does that work? And you're like, oh, let me just show you an example. And they'll be like, oh, right, that makes sense. Okay, examples are really good justification at this age level for a lot of things, actually. You don't always have to actually have a full-out proof. That's not the point. The point is a justification. This one was supposed to be subtraction. So again, we're going to do a proof by justification by example, I don't know, whatever we're going to call it, but we're just justifying, not really proving. We're going to do a to the 4th over a to the 1. Okay, so a to the 4th means that I have 4 a's multiplied. A to the 1 means I have 1a. And if you have done anything at this point, which you would have if you've encountered exponents, if you've done anything at this point with division, you recognize that these two will reduce from a fractional standpoint, leaving you with 3 a's, otherwise known as a cubed. And how do you get from 4 and 1 to 3? Subtract 1. Make sense? Okay. The third one is the one we said that was multiplied, so a to the m to the n. And our justification by example, we're going to use the same, 3 and 2 we had before, a to the 3 to the 2. Okay, so a to the 3 means I have, good grief, I have a written down 3 times, and squared. And then the square means that I have the AAA written down 2 times. So how many total A's did that give me? 6. So this is a to the power 6. And what do I have to do to get from 3 and 2 to 6? Multiply. The last one says that I'm able to distribute the exponent. So we're going to do AB cubed. So AB cubed means that I have AB times AB times AB. Agree? How many A's is that? 3, so that's A cubed. And the number of B's is 3, so it's B cubed. Now, what I actually used in that last step, although we didn't really think about doing it, is I used the associative and the community properties. I reorganized so that all the A's were together, and I reorganized so all the B's were separate by using commutative, which means switching them around, and reusing associative properties to associate what I want to have grouped together. Okay, so as you're doing these problems, the goal is not for you to have to write out what I just did to justify them. The goal is to use the properties, okay? So here are a couple of examples of using those properties. The first one, I want you to notice that they all say base 5, right? 5 to some power, 5 to some power, 5 to some power. That's important because all of our properties hinged on having the same base. On part B, they don't have the same base, which means we're going to have to think about that problem a little bit differently. But on part A, it is a direct application of one of our properties. What can I do to simplify this? Add the exponents. So I have the same base. The base doesn't change. I don't multiply the 5s together. That's not what I'm doing. The exponents are the multiplication pieces. And there are 10, 2, and 4. So what is 10 plus 2 plus 4? It is 16. It's okay? All right. So as I mentioned, you can't just plow through on part B because they don't have the same base. They're different bases. But what I can do is I can break the number 6 into its factors. So what does 6 break down into? 2 and 3. So what I really have is I have 2 times 3 to the power of 4 times 2 cubed times 3 cubed. Do you see a property that I can use? You can use property number 4 that distributes the power to each of the pieces. So this is 2 to the 4th. And then I have 3 to the 4th. And then I have 2 cubed and 3 cubed. Again, I can do some reshuffling of the terms, commutative and associative properties. And I can group these 2's together. How many 2's do I have? 7. How many 3's do I have? 7, yeah. I have 2 terms that have a 3 base, right? But then I have 7 as the exponent. No, they wouldn't even have to have the same exponents for this problem to have been worked out this way. This one just happened to. All right, so far so good? Okay, I think I have time for 1, maybe 2 of our multiplication properties, and then we'll pick back up on Monday where we've left off. All right, multiplication properties are some of my favorites, not properties, but algorithms, because there are quite a few of them that are quite different from one another. Whereas with addition and subtraction, we just had a few things, and they kind of resembled one another. We had a standard algorithm, an expanded algorithm. We had equal additions. That's about all we had. We had a concrete model too, I guess. These are uniquely different. So the first one is expanded algorithm. This one is my favorite because I feel like it's very intuitive about what it does. So you're going to draw a box. The box needs to have as many rows and columns as the numbers are that you're multiplying. So these are a 2 by 2, right? I have 2-digit numbers, and there's 2 of them. So we're going to make 2 rows and 2 columns. It's going to be a grid box that looks like it's split into fourths. The number's 48, so I'm going to write, I'm totally doing the next one. Let me copy this to the next page. I'll come back to this one. Shift what you're doing. This is partial products. Just relabel them for your paper. Partial products is what I'm doing. This is 40, and this is 8. And then we have the number 30 and the number 2. So this kind of feels like breaking up and bridging when we were looking at that like mental strategy. Each of the boxes is the multiplication of the row and column you're on. So this first box here is 40 times 30. This is 1,200. This second box is 8 times 30. That's 240. So why is this a good method? Well, this is a good method because it's really doing single-digit multiplication with some zeros tacked on at the end, right? If I'm multiplying 40 times 2, I'm really multiplying 4 times 2, which is 8. And there's 1 0 to tack on. And then I have 8 times 2, and that gives me 16. And then what I do is I add up all the values that are inside the, whoops. Let's try that again. Add up all the values that are inside the box. Now you can write them separately to do that if you wish. If you can do that without having to write them separately, that's fine too. But we have 1,200, 240, 80, and 16. And if we add those up, which we've looked at a lot of strategies for adding them up already, we will end up with a sum of 1,536. Let me go back to expanded algorithm then, because that one's actually the one that I skipped. I apologize. Got just on the wrong line of my notes. It still breaks them apart like that, 40 plus 8 and 30 plus 2. But it does it without the box. It sounds sort of funny, but it does it more from a standpoint of traditional multiplication. I make sure that I multiply the 8 and the 2, that gives me 12. The 40 and the 2, that gives me 80. And then I make sure that I multiply the 30 times 8 and the 30 times 40. 30 times 8 is 240. And then the 30 times the 40 is the 1,200. So you get all the same pieces, you just don't have the visual grid along with it. And of course, we still get 1,536. But you're thinking it more like you do with standard algorithm. I know we're at the time, but I want to show you real quick why the standard algorithm is confusing. So just listen to me talk through it, because you've seen this thousands of times in your life. We do something like this and we say, what is 2 times 8? And we say 16, and we go, okay, I wrote down a 6 and I carry a 1. This is what we say. And then you say, what is 2 times 4? 8. And then all of a sudden you're adding in the middle of a multiplication problem. And you get a 9. You're added in the middle of a multiplication problem. That's awkward. Then this mysterious 0 shows up out of nowhere. And it's not really explained very well where it comes from. It just shows up. And then we do the same thing again, and we say, okie dokie, now I have the 3 times 8, that's 24. And I hope that I rewrite the 2 on top of the 1 so that I don't confuse myself and not know what number's on top. And then once again, in the middle of the multiplication problem, when I do 3 times 4 and get 12, I add a 2.
I can see how that's confusing.
Okay? There's a lot going on in the middle of this problem. And I get, of course, the 1,536. Now, is it more efficient? Absolutely, it's more efficient. And is there reasons where the 0 came from and why we added in the middle of the multiplication? Absolutely there is. But it may not be the most intuitive thing to be describing or teaching as the first way of teaching multiplication.